I'm David Lindell, and for the past few years I've worked as a PhD student in the Stanford Computational Imaging Lab on a new type of computational camera that uses emerging sensor technologies to detect single photons with picosecond accuracy. The potential benefits of this camera are tremendous. We can capture scenes at the speed of light, measure geometry with just single captured photons, and even see around corners or through scattering media. My research has focused on combining computational techniques with these sensors to enable each of these applications. Let me show you what I mean by capturing scenes at the speed of light. This scene consists of a fiber optic cable that glows when you send light through it, and to one end we attach a picosecond laser that sends in short pulses of light. Our camera timestamps the photons scattering out of the fiber, allowing us to assemble a trillion frame per second video, recording the scene essentially at the speed of light. We call this type of video a transient image because it captures light transport at ultra-fast timescales. Transient imaging is incredibly useful for understanding light transport in a scene and is the basis of 3D imaging techniques like LIDAR. With LIDAR, we can acquire 3D geometry by measuring the time it takes for a pulse of light to travel to a point and back. While LIDAR has emerged as a key technology for autonomous vehicles, a key challenge is how we can image at long distance with very short exposure times and few returning photons. In my work on single-photon 3D imaging, I showed that combining LIDAR with data-driven techniques and sensor fusion with conventional cameras allows us to outperform existing methods and capture 3D geometry with only a single photon measured from the laser, on average across a scene. This type of technique could allow self-driving cars to respond quicker by letting them see further and scan faster. But what if our self-driving car comes to a blind turn and needs to see around the corner? In my research, I developed computational algorithms to make this practical. In this experiment, the single photon camera is located around the corner and scans the side of a building with a laser. We then measure the ripples of light scattered back to the building by the hidden scene over picosecond timescales, and our computational algorithm recovers their shape. So with this camera, we can see around corners, but we can also see through scattering media. A key challenge not only for self-driving cars, but for biomedical imaging and remote sensing. By combining the single photon camera with a new computational algorithm, we can capture a transient image and process it to see objects hidden behind a thick scattering barrier. With the computational single photon camera, we can see light in flight, infer geometry from single photons, and perform feats like seeing around corners or through scattering barriers. These abilities could be transformative for applications in remote sensing, robotics, autonomous navigation, biomedical imaging, search and rescue, and more. So while imaging at the speed of light might seem impossible, it really is just around the corner. Thank you.